This is a lesson in calculus-based kinematics about 2D velocity and acceleration, how velocity and acceleration can be analyzed in 2 dimensions using trig. As a reminder, I'm going to put up the equations here for average and instantaneous velocity. Average velocity is the displacement over time. Instantaneous velocity is the time derivative of the position vector. And this is a vector. Lots of times this is done in only 1 dimension, but we could possibly do it in 2 dimensions. And so the problem I picked out has to do with taking that time derivative of a position function. So the problem that I chose gave r, an object's position in meters, is given by the equation as a function of time in seconds. So technically, I guess this should be r of t. And what I'm going to notice is there's these hat notation in here. I hat means in the x direction and j hat means in the y direction. If there was a k hat, that would be in the z direction. And it asks, what is the object's speed at 60 seconds? Well, if I want to look at the speed, that's the absolute value of the velocity, the total velocity vector. So I'll take the absolute value of that. And I'm going to remind you, well, if I have x and y components, then I would want the velocity in the x direction squared plus the velocity in the y direction squared and square root it, just like Pythagoras would tell us to do, right? If I have 2 components, and I want the resultant, I would take those 2, square them, and add them, and take the square root. So that'll be the ultimate strategy for finding the speed, but they give me the position function, and so I need to find these individual terms vx and vy. So what I'm going to do is I'm going to take the time derivative of each one of these separately, right? If I do dr dt, well, I'm going to go d by dt of the x component, and I'm going to do d by dt of the y component, or the j component, whatever you want to call that, all right? So the time derivative, I'm going to have the time derivative of a linear function, 0.5t. That won't be too hard to do, and that'll be in the I hat direction. And then I'll do the time derivative of what's in the y direction, 0.02t squared, and I'll leave the j hat there. Okay, so let's take the derivative of the I hat component. The time derivative of a constant is 0. The derivative of t is just going to be 1, so I get a negative 0.5 in the I hat direction. And then in the other part here, derivative of a constant is 0 plus, well, t squared, I'll bring the 2 down and multiply that by 0.02, so I get 0.04. And then that leaves t to the first power. I'm not going to write the 1, and that's still in the j hat direction. So this is the velocity vector as a function of time. There's time in only one place here. So if I wanted to find the velocity at 60 seconds, right, like it mentioned up here, what is the speed at 60 seconds? I'll get 2 components. Well, the x component in the I hat direction doesn't depend on time, so it's going to stay the negative 0.05 or 0.5. And then I'm going to plug in 60 where I see t in here. So 0.04 times 60. Well, that's 24, but you move it over a decimal place. It's 200. 4 times 60 is 240, and then move it over 2 decimal places. So 2.4, and that's in the j hat direction. So if I thought about this velocity vector, it would be negative 0.5 in the x direction, and then a positive 2.4, 0.5, negative 0.5, and a positive 2.4 in the y direction. So the resultant vector here, let me draw the resultant vector here, it's going to look like this. Okay, and what they're asking for is what's the magnitude of that, right? What's the magnitude of that? So let's finish out this calculation. I have these two components. Now I can just plug them in up here. The x component is negative 0.5 quantity squared plus 2.4 quantity squared, square root it. And that will give me the speed of the object, okay? When I run this through the calculator, I get that the speed should be a little bit more than 2.4, right? When I look at this Pythagorean theorem, the vector here, I have 2.4 on one side and 0.5 on the other. Well, that's going to be a little bit more than 2.4. So I get 2.45153. You can round that. Seems like there's what, one sig fig up in here, but that would be how you calculate that. So pretty straightforward. We're using that time derivative in order to find the velocity from the position. And here we're using the x and y components. I think it's when you're not used to that notation and that strategy, it can be a little daunting, but now that you see it, Pythagorean is not too hard to do. Another problem in here that I chose to deal with velocity as a vector has to do with a change in velocity. A particle's initial velocity is 100 meters per second directed 65 degrees above the horizontal. Over time, this velocity changes. This change in velocity, delta v, is 90 meters per second directed straight down. What is the particle's speed after this change? So what I am seeing here is that we're given an initial velocity and velocity vector, and it wants the speed, which is going to be the final velocity vector, the magnitude of the final velocity vector. How do I get from the initial to the final velocity vector? Well, I'm going to take the initial velocity vector, add on this change in velocity vector, and then that will equal the final velocity vector. So this, I think, makes sense in sort of an equation sort of way. Let's look at the vectors here. It says that the initial vector is 100 meters directed at 65 degrees. So let me draw that in here. Here's V initial. I'm just going to put this 65 in here above the horizontal, and that's 100 meters per second. So V initial, the delta V is 90 downward. So I could draw it here, right? I'm just adding vectors. So I could draw it straight downward, delta V, just vector addition. So when I look at this final velocity vector, it will be represented adding head to tail, those two vectors. There's the final velocity vector right there. And we want to find the magnitude of it. So what's the easiest way to do this? Well, I'm going to do what I've done before with 2D vectors, is decompose them into their x and y components, and then add the components, and then resolve those components into the final magnitude of that vector. So I like to do this with a chart. I'm going to do that over here on this right side here. I know that I'm going to take V initial. I'm going to add on the delta V vector, and then when I add those two together, I'm going to get the final. I'm going to note that there's x and y components. If there was also a z component, I would do a z column over here, but I don't need it. Let's do this. The initial velocity vector has an x and a y component. The delta V has no x component. It's only 90 downward. So I'm going to fill in that part of the chart first, right? 0 in the x direction, 90 downward. Okay, so that's for the delta V vector. The V initial vector, you may have done this on your head, in your head already. This will be 100 cosine 65, and this will be 100 sine 65. So when I add those two vectors together, I'll add their x components and their y components separately. So the final velocity has an x component of 100 cosine 65. That makes sense. The change in velocity vector did not cause any change in the x direction. It caused it only in the y direction. So this will be 100 sine 65 minus 90. I went ahead and ran these through my calculator so I can have some tangible numbers to work with at this point. You don't necessarily have to, but it's nice to do that, I think. So 42.262 there. And this was awful small. I think it depends on what randomized numbers you get in here. If you get, I saw another problem with 67 degrees, and these were a little bit, this was like 2 point something, but that is what it is for my numbers. And so I have those two components. And I'm going to do what I did on the previous slide. If I want to find the magnitude of the final velocity vector, I'm going to take the Vx and square it and the Vy and square it, and then that will give me the magnitude. So I will take 42.262 squared plus 0.631 squared and take the square root. And when I run that through my calculator, that the magnitude of that final speed is 42.267 meters per second. Okay, so the physics here isn't too bad. I'm just taking initial velocity vector, adding a change, and getting a final velocity vector. Nothing too spectacular about that. We're adding vectors like we've done before with position or relative motion velocity. The technique of the using a chart with the columns is pretty slick trick there for you to be able to move the problem through the problem and keep everything organized. And then this is a common strategy that we'll keep in mind with vectors that have been decomposed into their composite vectors. Okay. So that's velocity. Let's look at acceleration. Acceleration has very similar traits here. It is a time derivative. It's a time derivative of the velocity. I have that down there. We can take the change in velocity and divide it by the change in time, and that would give us the average acceleration. If we wanted an instantaneous acceleration, that would be the time derivative. We could do a double time derivative from the position vector. The first derivative gives us the velocity. The second derivative gives us the acceleration. Okay, so acceleration is a vector like position, and it's a vector like velocity. So it could have an x component, a y component, and a z component. So the problem that I chose here talks about having an initial velocity vector and a final velocity vector that changed over a period of time, and they asked us for the average acceleration. A particle's initial velocity is 30 meters per second directed along positive x. Okay, so I'm going to draw that here. Let's do a straight vector. Here's 30 meters per second. That's v initial, directed along the x direction. 6 seconds later, okay, words mean things, 6 seconds, its velocity is 50 meters per second, directed 70 degrees above the x-axis. So I'm going to draw a little bit bigger vector here. So there's v final, and it's directed at 70 degrees. What is the magnitude of the particle's average acceleration? So on the prior slide, I had this. The average acceleration is the change in the velocity vector over the change in time. Okay, so what I'm going to do is I'm going to find this change in velocity vector. I have a v initial and a v final, and we saw before v initial plus delta v equals v final. So if I want to solve for delta v, I would take v final and subtract off v initial. So when I set up my chart over here, you probably already saw that coming. I'm going to set up a chart over here. And I'm going to take v final, subtract v initial, and that's going to give me my delta v. Okay, and I left room for a couple of columns. There's x, there's y. V final, I'm just going to fill in the components in here. V final has an x and a y component. The x component will be its magnitude times cosine 70. So I'm going to get 50 cosine 70 here, and this will be 50 sine 70 there. Okay. V initial was only 30 in only the x direction. It has no y component. So when I find delta v, I'm going to take v final minus v initial. So I go 50 cosine 70 minus 30, 50 sine 70. So that's the delta V. This is delta Vx. This is delta Vy. I ran these through my calculator. This I got a negative number, negative 12.899. And this I got to be 46.985. So I have those two numbers. So like I said, this final second to last step here, delta V, the magnitude of that change in velocity vector is going to be delta Vx squared plus delta Vy squared and square root it, right? This is the x component. This is the y component. Watch out when you run this through the calculator. You want that negative sign on the inside of your parentheses so that the two magnitudes add together of those squared terms. Okay, and then I'm going to take a square root here. And when I run that through my calculator, I need a delta V. Delta V, the magnitude of that change in velocity is 48.723 meters per second. I'm not done yet. They asked for average acceleration, so I'm going to take that number and plug it in over here, 48.723, divide by, remember words mean things, the 6 seconds. 6 seconds it happened over, and so the final answer here becomes 8.121, and units of acceleration is meters per second squared. So that's your answer on this problem. Again, in review, I use the change in velocity, right? V initial plus delta V equals V final. And I just rearrange that equation to get the useful form for this problem. Once I had that, I set up my chart to be able to add or actually subtract these two vectors, right? I was subtracting these two vectors to find that delta V. Again, I use the Pythagorean theorem in order to resolve those two components into the resultant vector, and then when I had the magnitude of the resultant vector, I just divided by time to find that acceleration. So again, with velocity and acceleration vectors, if you're doing it in 2 dimensions, you just divide into the x and y components. And what I'm finding and what you saw on all of these problems is to draw the vectors and get their components going and get some way to methodologically consistently add or subtract the vectors. And then Pythagoras is still around thousands of years later. So good luck and have fun on these problems.